So let's talk a little bit about this. We're going to have to basically move on at this point. We got a long way through this exercise. Let's talk a little bit about the results. What did you all expect to happen here? What did you expect the trend to be? Yes?
Based on that PowerPoint?
Yeah.
We thought the smaller ball was going to go farther.
You thought it was going to go farther?
Now, obviously, looking back on it.
Yeah, okay. So why did you think it was going to go farther?
The smaller ball?
Yeah.
That's what I'm confused about.
Okay. So remember what I said. I mean, part of what this exercise has a little bit more sophisticated physics going on in it than it could. We kind of did the next exercises we're going to do here are a little simpler. This one's a little more complex. So a lot of you thought. So let's talk about why you thought the smaller ball would go farther first.
Because it has less mass and with the same force it will go. But, the aerodynamics on it, the resistance of the air, on a small mass, really held it back going farther. Then the bigger ball, where the resistance didn't act as much as on the smaller ball. So,
Okay, well, let's.
the aerodynamics.
A lot of interesting ideas there. So, one of the ideas that just came out of this comment is that. So there's the force that you're throwing with, but then there's another force that was just described. What's another force involved?
Wind resistance,
Air resistance. Yes, ma'am.
Well, you also have to think of the composition of the ball that you're throwing. I mean, it's a styrofoam ball,
Okay.
so it's got different surface area. Every time you throw it, it drops. It changes shape, even though you don't want it to. It's not a solid mass because it's aerated, and I mean. Whatever. It's got those little.
Yeah, it's got holes in it.
Thank you, porous.
Yeah.
So I mean.
Yeah, there's a lot going on there. But let's go through that. Let's go through the process. Is there a styrofoam ball? Where's the ball? So let's think about the process there. So I think we have to be careful about when we talk about forces in this case. When we throw with a certain force, is that force on the ball the whole time?
No.
So when is it on the ball? Okay, up until the point when you release. That's a great way of putting it. So up until the point when you release, you're applying force. And then as soon as you let go, it's no longer there, right? That force. So what's happening from that point on?
Velocity.
Gravity is taking over.
Friction.
Okay, it's complicated what's happening from there on out. We've got slow, it's complicated what's happening from there on out. But if I can, this is where, when you first learn physics, like at the undergraduate level, one of the first things you learn about is ballistic motion, which is, all that means is the way a baseball flies through the air, right? It's just the motion of a ball flying through the air. And one of the first things we teach students is to try to separate your thinking in the horizontal and the vertical direction. So, in the vertical direction, what force is on the ball? Okay, so that's what's pulling it down, right? In the horizontal direction, what's happening? What is the force on the ball in the horizontal direction? Yeah?
We were just thinking myself.
Oh, okay.
Friction.
Well, friction and air resistance, friction is a type of air resistance, yeah?
There's still a force left from the ball itself that's pushing itself forward or something.
Okay.
There's still something from where you let it go. The force is transferred from your hand to the ball. I don't know.
Okay, well, let's talk about that. All right, so you're wondering why is the ball moving if there's no, why is the ball moving forward if there's no force pushing it forward? That's precisely what inertia is. Inertia is the tendency of an object in motion to stay in motion. Okay? So even though the only force on that object is in the opposite direction, it's still moving forward because of inertia. That's correct. Okay? Eventually that force will bring it to a stop. but it's continuing to move forward. And what's happening? What's happening to its velocity forward? It's increasing, right? Motion forward is decreasing. So now let's get back to this. Okay, so maybe I should draw this. So we have a ball going through the air. All right, its motion is forward. What are the forces on the ball going through the air? You already said there is something. I'm going to draw. How many arrows am I going to draw on this? Yeah, read my mind. How many arrows?
One down and one
Four. 4 arrows.
I'm hearing 4, 3.
Four.
Let's start one at a
2,
time.
4.
All right. So, but I mean, this is the ball in the air, mid-flight. Which direction is your gravitation force?
Down.
All right.
And one at it, in the opposite direction that it's traveling.
Does everybody agree with that?
Yes.
So it's moving this way. What's this from?
Air resistance or friction.
All right. So there's people that were saying 4. Where else do we got?
Inertia, that way.
Okay.
But inertia is like in the air.
So let me. So let me say something that is going to be a little confusing. Inertia is not a force. Inertia is what resists force. Okay. I would claim this is all the forces on that object. That's it.
Then why is it moving forward?
Aside from what? Oh, aside from, well, is there, so you're talking about like air pressure?
Yeah.
But is that a net force on the side?
No.
That's all net you said.
Yeah, okay. You got it. You got it.
I asked the same question to her the other day. I observed the teacher, and I said, she said something that might be, misleading to the students, but because it's such a higher level, you just kind of let that go. But you're right.
So I don't know if everybody heard that. It is an important point. There are other forces on this object. There's air pressure being applied from every direction equally. That's not a net force, and it doesn't affect the motion of the object. Does that make sense? Yes, ma'am.
So the force ends when you let go of it?
Yep.
Well, the force of your hand ends when you let go of it.
The force
There's
That's
still-
what that forward force
Correct.
ends.
So it's not terminology thing, it's going from force to inertia, and that's what's about after that, or what?
No, it always has inertia. A ball. Let's think about outer. Okay, so this is where you get in trouble when you talk to a physicist, because I'm going to ask you to imagine an imaginary place out in outer space. All right. Imagine there's no air resistance. Okay. All right. Yeah. So if we're in outer space, you're on and you push this ball with a certain amount of force and you let go. What happens?
It would continue on and on and on and on.
Okay, so there's no force on the object once you let go, and yet is going to continue forever. That's why. So the first law sounds simple, but you got to read it and you got to trust it. If there's no force on the object, it will continue without stopping. Yes, ma'am.
So, but if it were to bump into something,
Yeah.
then it applies a force, is that right?
Yeah, that something will be applying a force to it. Absolutely.
But if it pushes something out of the way, doesn't it have force then?
Yeah. Okay. So again, it depends on what perspective you're looking from. Are you looking from the thing it's pushing or the object itself?
The object itself.
If the object itself, it pushes off something, that something is going to give it a little force, and that will affect its motion. It might stop it. It might deflect it in a different direction. You're not buying something.
It just seems like if it's flying through the air and it hits something, then didn't it have force to
It
move that
applies
object
force
out
to
there?
that object. I see what you're saying. You're
But-
saying
So
I
it
understand
has
what you're
energy,
asking.
but that's not called a force.
I know what you're asking. So I'm beginning to understand what the confusion is here. Because you're saying to yourself, okay, you're telling me there's no force on this object. It's just inertia. And yet, if it hits something, it's going to apply force to something else.
So is it just a transfer of energy now, and not really a force? I mean, if it's...
But doesn't that translate to its mass? Wouldn't that be an example of that picture that you showed us with the arrow going this way and then the other thing coming this way?
But doesn't it become a force in its new system?
I mean, the way of looking at it is that it's got a tendency to, when it bumps into another object, that object is going to change, it's going to do something to that. The ball has inertia, it doesn't want to change its state of motion. And in order to change its state of motion, that object's got to apply a force on it, and it in turn applies a force on the other object. This is a good question. I mean, the way you guys are thinking about this is actually, I mean, it's a different way of looking at it that it's hard to answer. You're saying, is it a transfer from inertia to force?
So, but we would say it doesn't have a force until it interacts with something else, and then we would say it's applying a force.
And the reason it doesn't have a force, so this again gets down to the F equals ma. All right, and I don't want to go. When it's moving through the air, I mean, I'm going to use equations occasionally. That's what I'm going to do. The F equals ma. So does everybody understand what those symbols are? F is force, m is mass, and a is acceleration. When it's moving through space without changing, when it's moving in a straight line, what do we know in this equation? What do we know about this? So I'm describing motion.
Its mass and its acceleration are constant.
Well, its acceleration. A equals 0 is exactly right. Okay? So when you look at this equation, here's one way of thinking about this equation. This is the motion. This is the force, of course, and this is the inertia. The motion, so A equals 0 in this case, which means force on that, the net force on this object is 0. As soon as you hit something, this no longer is 0. Now, there's acceleration. One thing is decelerating, another is accelerating. And so now there's forces all over the place. Okay? It's a good question.